Yeah, so here to talk about our project on designing and fabricating and testing a three-electrode electrochemical cell with an integrated pressure sensor. Um, so a little bit of introduction. So an electrochemical cell is kind of the main characterization tool or technique that we use to characterize lithium ion or other battery systems, lithium sulfur included. And so typically that consists of a two-electrode cell, usually in a coin cell format, so where we have an anode and a cathode, and then by applying either fixed current or stepping through voltages and measuring the applied changes in voltage or current, we can track changes in the electrochemical track electrochemical processes going on within the battery. So during charging and discharging, you have these lithium ions that travel back and forth and shuttle between the anode and the cathode. And so by measuring the voltage, changes in voltage, we can look at the physical processes going on and try and get an understanding of the different reactions going on within the batteries. And another tool we've got, so in a full cell, when we're trying to measure the potential difference between these two electrodes, because in a full cell, both materials will have a changing a voltage. It's difficult in a two-electrode cell to kind of isolate which electrode is causing sort of when you cycle these materials, which one is causing the failure of the battery. So what we can introduce is a third electrode, a reference electrode here, typically made of lithium metal, which we don't pass any current through. So then we can measure the potential difference between both electrodes separately. So between the reference electrode and the cathode, and the reference electrode and the anode. And through that, we can track changes independently with both electrodes and gain deeper understanding as to which electrode is causing issues within the battery, because this is important to test full cells. So typically we test a lot of materials just in half cells, so we measure one electrode versus a lithium metal electrode, but it's important to test full cells as well, because the degradation mechanisms in full cells can be quite different to half cells. So within our project, we basically aim to take this three-electrode cell and integrate a pressure sensor with it. And to our knowledge, to our best knowledge, at the moment, that in the literature we've not found any sort of examples of a pressure sensor being integrated into a three-electrode cell. And so this integrating the pressure sensor allows us two sort of main benefits. So the first being when we assemble the cell, the stack pressure, so the pressure applied between the anode and the cathode, is quite important, because if it's too low, then we introduce extra ohmic resistance, and if it's too high, then we sort of reduce the battery performance. So it's really key to get kind of an optimum pressure between the two electrodes, and this is we think dependent on the battery chemistry used as well. So it's a good idea to be able to test this for different battery chemistries. And the other main benefit I'll show to you with a couple examples is we'd like to try and do some in situ monitoring. So basically monitoring the changes in pressure as we test the battery, as we cycle the battery. And so this is really interesting, particularly in terms of silicon anodes. So this is one of the materials I'm working on in my PhD. And so these are interesting materials because they can store 10 times more lithium, 10 times more energy than conventional lithium-ion batteries. And they do this through a series, well, you can store a lot more lithium, and the reaction occurs. You start with crystalline silicon, and as you lithiate silicon, you go through these amorphous phases, eventually getting to this crystalline Li15 Si4 phase, where the silicon is expanded by around 300%. And the other interesting thing is we get at low voltages, you get this electrolyte breakdown layer, so the solid electrolyte interphase, which is the electrolyte that breaks down and forms this passivating layer on the surface of the silicon. And then in subsequent cycles, as you re-lithiate the silicon again, so it contracts when you delithiate, and then expands again as you relithiate it. And this SEI layer, the solid electrolyte interface layer, is quite fragile, and it fractures and breaks when you re-expand the silicon. And when you expose fresh silicon surfaces, you get more SEI forming on the surface. And over multiple cycles, you get this expansion and contraction of the silicon and sort of continuous SEI formation. And this is eventually what leads to the death of the battery and increases in impedance and everything. And so we have many sort of strategies to try and mitigate this pulverization and try and improve and extend the cycle life of silicon anodes. And but really, we think including a pressure sensor would be really interesting to try and monitor these changes in pressure and try and correlate these to the volume expansion and try and gain further insight into battery failure mechanisms. I'll hand over to Liam for.
Yeah, so a second example that we've looked at is in lithium-sulfur batteries, which are, again, different from conventional lithium-ion batteries that are currently used commercially. They use a sulfur cathode inside a conductive matrix, which is usually made of carbon or some kind of porous conductive material, and they're able to store about 5 times more energy per unit weight than a conventional lithium-ion battery cathode made from metal oxide, such as cobalt oxide. And these store energy through the conversion of elemental sulfur, which is sulfur 8, to lithium sulfide through a series of stepwise reactions, which are indicated within the electrochemistry, which you can see on the left here as a series of different voltage peaks. During the conversion of elemental sulfur to lithium sulfide, there's a large decrease in density. So the lithium sulfide occupies 80% more space than the elemental sulfur, which leads to an increase in the volume. And this impacts on the conductive host matrix because it applies a load which can lead to fracturing and loss of electrical connections. Another load that can affect the electrical connections is due to the redeposition of these polysulfides, which are soluble in the electrolyte and which shuttle between the 2 electrodes as they dissolve. So something else, similar to the silicon electrodes, the lithium sulfur cells are also affected by the applied stack pressure, which is illustrated in this electrochemical image on the left. So the light green color corresponds to a low applied pressure, and then the darker blue color, which is the highest current, and is shown here, is for a higher applied pressure, and this corresponds to improved electrical connections. So clearly controlling the pressure applied for cells that are otherwise exactly the same in terms of the electrode composition has quite a big impact on the cell performance. Okay, so go to the next slide, please. Okay, so looking at the design of the 3-electrode cell, it's a kind of cylindrical external holder made from PEEK, which is a electrochemically inert and also chemically inert to the different electrolytes that we're using. And this contains the 2 electrode contacts, which are made from stainless steel, which is again electrochemically inert and doesn't participate in the electrochemical reaction at all. We can then apply pressure through the 2 caps, which are shown at the top and the bottom. And then at the bottom of this image, you can see the sensor with the black cable coming out of it, which doesn't have to be installed when we're assembling the cell inside the glove box. So we don't have to put it through the vacuum chamber during assembly. Looking at the 3D view on the right, I'll talk a little bit more about the electrode configuration on the next slide. But this is looking down what is the top of the cylinder on the left of the slide. And these are the 3 different electrode contact points. So I guess clicking again, we can see that the sensor is then inserted at the bottom. So one of the 2 kind of T-shaped cylindrical contacts, then has a small cylinder that protrudes through the bottom and presses onto a kind of button on the top of the sensor, which then measures the applied load. Okay, so looking at the two different configurations of electrodes that we tried, as Dylan mentioned earlier in the presentation, normally when we test electrochemical cells in a kind of coin cell configuration, we only have the cathode and anode contacts at the top and bottom of the coin cell. So we experimented with a couple of different configurations to see which is the best position for the third electrode. And in both instances, contact was made through a copper wire, which was inserted through one of the kind of cylindrical things which you can see protruding out of the side of the main cylinder. So looking at the two different configurations that we're referring to, there's the kind of T configuration where the reference electrode sticks out the side, kind of like the base of a T, with a piece of lithium twisted into the copper wire, which has two separate cables. And this is the one that you can see in the top right of the photos, with a piece of lithium highlighted in red. Yeah, thank you. So this is kind of within the, in line with the, kind of perpendicular to the direction of the main electrode stack. The other configuration that we looked at is the external reference electrode, where the reference electrode is kind of external to the main electrode stack, and the contact is made through the center contact point using a copper wire beneath the copper current collector on the anode. This has the advantage that there's kind of inherent control over the distance between the reference electrode and the rest of the stack. It does have a disadvantage in that we need slightly more electrolyte to make sure that there's electrolyte contact between the reference electrode and the rest of the cell. And this can mask some of the degradation mechanisms that we want to look at when there's excess electrolyte. Yeah, so the photos on this slide show what it was like to assemble the cell ergonomically inside the glove box, where there's quite limited dexterity. But it was, in terms of the difficulty, it was very similar to assembling a standard coin cell. Yeah, and then in the bottom right, you can just see the first cell that was assembled, and it had a non-zero open circuit potential, which indicated that it was working okay. Thanks. So in terms of monitoring the pressure sensor and synchronizing the data with the electrochemical data, we have this load cell which is integrated in the bottom of the cell and connected to a Raspberry Pi through a load cell amplifier circuit. And later on, you'll see that there's some noise in the data, and I expect that some of the noise comes from just the electrical connections within this amplifier circuit, which is hand soldered and then just connected to the Raspberry Pi. So we wrote a graphical user interface for some control of the electrochemical, of the sensor and recording of the data with a timestamp so that it can be matched up to the electrochemical data easily. In terms of calibrating the pressure sensor via the load cell amplifier, we had a series of different weights, so 0 grams, 50 grams, 100 grams, and 200 grams, and looked at the linear increase in the output voltage compared to the load that was being applied, and used this to effectively calibrate the load sensor. And then before each experiment, we take an average of the output of the load sensor and use that as a baseline. Okay. So as a starting point, we looked at a 2-electrode lithium sulfur cell, which is well characterized electrochemically in terms of this composition of electrode. So in the top right, that's top left, there's the electrochemical profile of the cell, which is then, if you can imagine that kind of being unraveled, this is kind of represented by the blue current line in the larger graph below it. So during the first 24 hours, which is represented by the part where there's high voltage that's kind of constant. This is where the cell was left so that the electrolyte could kind of percolate through the separator and through the electrode as well. And there's kind of a steady increase in pressure throughout this time, which is probably associated with like the absorption and the swelling of the electrode by the electrolyte by the electrode, and especially the polymer binder. Beyond this point where the voltage was then varied, there's a kind of steady increase in the pressure with time, and also some more localized increases and decreases in pressure as the current changes. And looking at the scatter plot in the top right, this is for the first discharge and charge cycle. And during the first discharge, the pressure change with changing current is positive. And this is theoretically associated with the formation of this lithium sulfide, which has a higher volume than the precursor, which is the elemental sulfur. And then during the first charge, the pressure then remains positive initially and then decreases. However, this kind of linear, steady increase in pressure with cycling and the non-ideal electrochemical performance of the cell that you can see. Initially, because of the spiky voltage profile, normally I would associate this with forming lithium dendrites. So in a lithium sulfur cell, the anode is always elemental lithium or lithium metal, which is different from a lithium ion battery where the anode is lithiated graphite. So it's quite easy for dendrites to form. And also this voltage profile is similar to the cells I tested previously where a low pressure was applied, which is also conducive to lithium dendrite formation. So it's tempting at first to attribute the failure of the cell and the poor performance to the formation of lithium dendrites. But the increase in pressure that we saw from the pressure sensor forced me to think about it slightly differently. And I think it's quite likely that actually the decrease in cell current with time and the corresponding increase in pressure was actually due to the deposition of lithium polysulfides at the interface of the cathode and the electrolyte, leading to an increase in cell resistance with time and a decrease in active material utilization, which would also cause an increase in the viscosity of the electrolyte and correspondingly more resistance in the cell and capacity degradation. So it was interesting to see a different perspective on what could be causing the cell failure that I maybe wouldn't have considered normally, that came from looking at the pressure data. Okay, thanks.
So moving on, we tested 3 different electrochemical 3-electrode cells. So both in the 2 different configurations that Liam's already discussed. So the first one we tested was in this T-cell configuration with the reference electrode on the side of sort of the inner cavity of the electrochemical cell. And so we did a similar test where we allowed the cell to rest and allow the electrolyte to percolate through so in this case we used a silicon graphene anode and an NMC, a nickel manganese cobalt oxide cathode material. And so we allowed the electrolyte to percolate through, and then on application of a current after 12 hours, we had a short circuit. So upon opening the cell, it looks like the reference electrode had contacted the NMC cathode material and short circuited. But even so, even looking at the pressure data, we can see so the initial sort of decrease away from the baseline, I think, is just through sort of connecting the cell. There's a small change. Possibly this is just we need to optimize how we're looking or improve the way we're taking our baseline value. But after this, there's a slow increase over around sort of 10,000 seconds, which we believe is because of the electrode swelling, the binder swelling, but also could be due to this SEI formation, that even though we're not cycling the battery, that I've seen examples of this within some other work that I've done of just that there's like a native SEI, we call it, that even before cycling can form on the surface of the silicon anode. So it's really interesting that we can see that even though the battery failed. So then we tried again with a different configuration. So this time with the sort of the reference electrode at the bottom and the sort of external underneath the full cell. And this time the open circuit voltages for the NMC in blue and the silicon in orange here were a bit more steady, but then when we applied the current after 12 hours, we had a short circuit, and we can see that the voltage fell below zero. So this is indicating that there is a lot of current being applied, and so as we opened up the cell, we saw that the lithium metal electrode here, so the shiny one, had been stripped. So when we compare that to how a normal lithium metal electrode looks like within battery, it has a sort of much more a dull color. So this shiny color is indicating that it did strip and expose fresh surface and deposited on the back of the copper current collector that's of the anode. So this is two interesting things from this is that we can see that our cell is definitely airtight, in that the lithium metal didn't react. So lithium oxide, if it did react with the air, so this is kind of a dull color as well, a whitish dull color. And we can see that again, we had this sort of change in pressure, so an initial increase, which is correlated with this increase in the open circuit voltage of the silicon anode, which is as the electrolyte percolates through this composite nano composite electrode. As the electrolyte percolates, the open circuit voltage should increase as the ohmic sort of resistance decreases. And then again, we had this slow buildup of pressure as this native SEI forms in the binder swelling. But then after that, the pressure remains very stable, other than the noise from the amplifier. So that shows that we're not having any electrolyte evaporation, which is a common problem with these different peak cells that I've worked with for different characterization, different testing. Yeah, and so then again on the third test, we again went back to this T cell configuration, and again unfortunately had a short circuit. So this time it was a slow kind of short circuit. So the looking at the counter electrode, the NMC cathode, we saw that there was a slow short circuit, and upon opening the cell, the NMC cathode had delaminated from its aluminium current collector. So and we believe that was because of the short circuit. But again, we still saw this slight increase in the pressure as the binder swelled and this native SEI formed. So these are really interesting things that we didn't even expect to be able to see, and allow us to sort of have deeper understanding of why these cells may have failed. So but in conclusion, we were able to design and test a novel electrochemical cell, which was easy to assemble within the glove box, and provided an airtight environment to test and perform electrochemical tests on 2 and 3 electrode cells. Unfortunately, in the 3 electrode cells, we still need to work on trying to optimize the positioning of the reference electrode, but in the 2 electrode format, we were able to get some nice data, that and the pressure sensor was sort of well matched in terms of sensitivity, and we were able to get some good insight into the battery in terms of native SEI formation, binder swelling, and dendrite formation, and it seems like at least in the 2 electrode format, just as a few tests to try and optimize the stack pressure, could allow us to have some nice testing of over long term to try and look at the changes in pressure in a 2-electrode cell. In terms of future work, like I said, yeah, we want to try and optimize this 2-electrode and 3-electrode configurations in terms of the reference electrode. And we'd also like to try and optimize the stack pressure. And in terms of deeper analysis of the battery, so right now we're just looking at the changes in pressure, but I think it'd be really nice to try and model the elastic modulus of the different components to try and understand changes in stress and strain, and correlate that back to the electrochemical data to provide deeper insights into the failure mechanisms. So yeah, that's our project. So thanks for listening, and any questions are welcome.
Thank you very much. It's a very interesting talk. I think the measuring in situ in an electrochemical cell is very important, and the application to the battery failure mechanism is a nice one. And I particularly encourage you to see you have covered the whole range from the device and then the cell module in situ measurement, and even now getting close to identify the relations and between the in situ pressure and the cycling. And I think that is a very nice work. Now, in the interest of time, we'll only have one short questions. Anybody? One short question. No? In that case, let's thank Liam and Dylan again. I'm sure if there's anything, you can contact them via email, or the CAPA office can help. Thank you very much.
Thank you.